Okay, welcome back. For the last part of today's session, we're going to talk about subtraction. We've already done addition, so we know how to add binary numbers and we know how to do it using digital circuits. So the next logical operation that we would want to consider is subtraction, which is the inverse of addition. Let's think about a subtraction problem. Suppose I want to subtract the following two base 2 numbers. The first number is 22 and the second number is 21, which are represented by 10110 and 10101 in binary. Now, this number is 22 and this is 21, so the result should be 1. If you're used to doing pen and paper subtraction in base 10, we can try doing the exact same process in base 2, and it turns out that this process works in exactly the same way. So let's go through it. First, we do 0 minus 1, which we can't do because we get a negative number. So instead, we borrow the 1 from the next place, which means that we replace it with a 0 and take the 1 and add it to the original place that we were working with. Now we have the number 10 in the ones place, which is the number 2 in binary. So this is 2 minus 1, which gives us 1. In the next step, we subtract 0 from 0 and we get 0. 1 from 1 gives us 0. 0 and 0 gives us 0, and 1 minus 1 gives us 0. So, as we predicted, 22 minus 21 gives us 1. And this works in binary as well as base 2. In fact, this works in any base. I could work in base 3, base 5, base 7, base 15, 16, whatever. And I would still be able to do pen and paper subtraction like this. The only thing that I need to guarantee for this to work properly is that the top number is bigger than the smaller number. In this case, 22 is bigger than 21, so this works fine. But let's say I have a subtraction problem like this. So how do we do this? This kind of process is the kind of thing that you could imagine emulating using digital circuits, but here we run into an issue. And the issue is that the solution to this problem should be a negative number. However, we haven't told the computer what a negative number is yet. So in order to do this problem, we need a way of keeping track of negative numbers. But the question is how? The problem is that computers only use zeros and ones. So the naive approach, which is just to take this negative sign and stick it in front of a number, doesn't actually work because, well, there's no negative sign on the hardware level. So I have to find some way of encoding the notion of a positive number and a negative number to a computer only using the digits 0 and 1. So we're going to spend the rest of this part talking about how to do this. Luckily, this is actually not so bad of a problem because since there is only two things I have to keep track of, positive and negative, and there are only two digits that I have available, 0 and 1, this gives a natural suggestion about how to define positive and negative. 0 should correspond to a positive number, and 1 should correspond to a negative number. So let's see how a computer scientist might make this work. The first attempt is something called 1's complement. And there are sort of three rules that make 1's complement work. The first rule is that one way to negate a number is to flip all of the bits. So if I have a number, and I flip all of the bits using NOT gates, I should get its negative. The second rule is that if a number starts with 0, it's positive. And if a number starts with 1, it's negative. And what this means is that this 0 at the beginning of the number and this 1 at the beginning of the number isn't actually part of the number. It's just a symbol that denotes whether the number is positive or negative. So let's try to do 1's complement with 3-digit binary numbers. First of all, let's look at 000. The first digit is 0. So this rule tells us that this number, whatever it is, should be positive. So to get the value of the number, we just take the binary value of the remaining two digits, which in this case is 0. For the second example, 001, the same thing sort of happens. 0 tells us that this number should be positive, and the remaining numbers are 1, so this should be 1. Similarly for 2, and similarly for 3. Now we come to the fifth number, 100. What is this number? Well, it starts with a 1, so it's negative. And if we negate this number, then we can figure out what the value of the number should be by looking at which positive number it corresponds to. So to negate this number, you just flip all of the bits. So let's do that. 100 becomes 011. 0, 1, 1 corresponds to 3. So this number must be negative 3. Now let's look at the next number, 1, 0, 1. We can apply the same process. This number should be negative. Flip the bits, you get 0, 1, 0, and this corresponds to 2. So this number corresponds to negative 2. And the same thing goes for negative 1. On the other hand, there's this last number here. So what happens here? So this number should be negative still, because it starts with a 1. And if we want to figure out which negative number it is, we flip its bits and we look at which positive number we get. But if you flip 1, 1, 1, you get 0, 0, 0. And 0, 0, 0 is the number 0, which suggests that this number should somehow be negative 0. But this is kind of a problem because negative 0 is equal to 0. So we've created a number system which lets us use positive and negative numbers, but it suffers from the caveat that there are two numbers which are equal to 0. If I tried to take this encoding method and actually use it in digital circuitry, you could build a computer that used the one complement system. But the problem is that you would frequently run into the awkward error, which is that 1, 1, 1 is equal to 0, 0, 0. And you would constantly have to keep checking for this. So it's not really a practical way of designing your whole entire system. So let's try a different system. This one's called 2's complement. And it turns out that this is the system that actually gets used in computer architectures and in computer hardware. 2's complement, again, is based on a similar set of 3 rules. But there's one difference, which is that to negate a number, you don't just flip all the bits. Instead, you flip all the bits and then you add 1, as if it were a normal binary number. So let's see what happens when we take a number and try to flip it. This number, again, is 0. Starts with 0, and so is positive. To get the value, we look at the next 2 digits, which are 1, 0, which corresponds to the number 2. So let's try to write negative 2. If this number is positive 2, we can use this method to negate it and get the binary expression for negative 2. So first we flip, and we get 1, 0, 1. Then we add 1, as if this were a normal binary number, and then we get 1, 1, 0. So the expression for negative 2 should be 1, 1, 0. Let's try another one. What about 0, 0, 0? This should correspond to the number 0. Before we had a problem where if we negated this number, we still got 0, but we had a different binary expression. So let's see if that still happens now. First we flip, we get 1, 1, 1. Then we add 1. And now something curious happens. We started with 0, 0, 0, which is a 3-digit number, but now we've got a 4-digit number, 1, 0, 0, 0. In our encoding system, we only care about 3 digits. And so I'm allowed to just ignore this number. I can pretend that in whatever circuit I'm using, I'm going to get rid of this output and just completely lose this output. So 0, 0, 0, once gone through this negation process where you forget the most significant digit, if there is an extra one, negates to 0. And this is good because now we have 0, and if you take negative 0, you just get the same binary expression for 0, which is what you'd expect. Let's try another example. 1, 0, 0. So this is a negative number because it starts with 1. Let's compute what its positive equivalent is once we flip it. First you flip it and you get 0, 1, 1, and then you add 1 to this number and you get 1, 0, 0. But this is kind of alarming because we started with a negative number, negated it, and then got the exact same number. So in 1's complement, we had the problem where there were 2 zeros. In 2's complement, you have the problem where there's this weird extra number, which is 1 followed by a bunch of different zeros. And when you flip it, you get the same thing. So on the face of it, it looks like we've just taken our one problem and translated it into another problem. However, this is actually fine, and we'll see why it's fine in a minute. Okay, here's the spoiler. We have to ignore this number, so I'll say why. So take a look at this table where we decode these 2 complement numbers into decimal. First of all, 0, 0, 0, 0, 0, 1, 0, 1, 0, and 0, 1, 1 decode into the usual 0, 1, 2, and 3 that we're used to from, well, normal binary numbers and 1's complement. Then we have 1, 0, 0, which I'll ignore for the moment. So let's look at 1, 0, 1. if you flip 1, 0, 1 and you add 1, first you flip 1, 0, 1 and you get 0, 1, 0, and then you add 1 and you get 0, 1, 1, and that's 3. So this should correspond to negative 3. The same thing happens with 1, 1, 0 and 1, 1, 1. If I flip 1, 1, 1, for instance, I get 0, 0, 0, and once I add 1, I get 0, 0, 1, which corresponds to 1, so this number should be negative 1. However, 1, 0, 0 is kind of the odd one out. It sort of makes sense that it's left out. If you look at the first 4 numbers, these have to correspond to 0, 1, 2, and 3. And these last 3 numbers have to correspond to negative 3, negative 2, and negative 1. But that means there's only 1 left. So whatever this number is, it has to be some whole number, positive or negative. But it can't have an opposite. Because whatever its opposite is would be some other number, and there's no more space in this table. So we just ignore this number. This does kind of look like a problem, because we have 8 numbers here, and one of them is useless. So that means we only have 7 numbers. But in practice, when you actually implement 2's complement, you might be doing this with 8-digit binary numbers. And 8-digit binary numbers, well, there are a lot more 8-digit binary numbers. So removing one of them, which behaves pathologically, is not so much of a big deal. So in the exercises, I'll have you play around with 2's complement with different numbers of binary digits, just so that you can get more familiar with how it works. Okay, now we've decided we have a system that lets us express negative numbers. And our original goal was to use it to do subtraction. So let's do that. Suppose a and b are 2 binary numbers. If I want to compute a minus b, one way to look at it is that this is the same thing as computing a plus negative b. Using 2's complement, we know that negative b is the same thing as flip b, which means b with all of its digits flipped, plus 1. So I've taken a subtraction problem, and I've translated it into an addition problem, with the caveat that I have to do a flip at some point. But the flip is fine, because we have NOT gates, and we know how to flip bits very easily using digital circuits. And the last note is that we ignore the last carry bit. So if you remember when I flipped 0, 0, 0 in the example, let me go back to it. I got 1, 0, 0, 0, and then I had to ignore this bit. So when you do the subtraction, you may have to ignore the last carry bit that you get. But that's fine, we can do that. And as I said, flip b means b with its bits flipped, which we know how to do. So let's look at an example of this kind of subtraction. Here's the same example as before, 22 minus 21. Now let's compute it using this method. So first we take b, which is 1, 0, 1, 0, 1, and we flip all of its bits. So we get 0, 1, 0, 1, 0, but then we add 1. So on the bottom here we have 0, 1, 0, 1, 1. Now you can just do this addition problem. 0 plus 1 is 1, 1 plus 1 is 0, carry the 1, etc. And if you do this out, you get 1, 0, 0, 0, 0, 1. And the reason that I put this leading term in red is that this number is the number that we ignore, which is the last carry bit, because we don't care about it, because it's not relevant to our representation of numbers. But this is great, because 22 minus 21 is supposed to be equal to 1, and if you ignore this last bit, then the number we got is 1. So this checks out. Now let's do another example. In this example, I'll start with the number 6, and now I'll subtract a bigger number. So this is the number 9. So I'm really doing 6 minus 9. So I should end up with a negative number after doing this subtraction process that I've outlined here. So let's do it. First, I take the bottom row and I flip the bits and I add 1. After flipping the bits, you should get 1, 0, 1, 1, 0, but then I add 1, so there's a 1 in the end. And now I can just do this problem. This one's fairly straightforward. You get 1, 1, 1, 0, 1. So this number should be 6 minus 9, or in other words, it should be negative 3. And the way to test that this is negative 3 is to pass it under the 2's complement procedure, which means flipping and adding 1 and seeing if we get positive 3. So let's do that. If you flip it, you get 0, 0, 0, 1, 0, and then you add 1, and you get 0, 0, 0, 1, 1, and this is exactly the binary representation of the number 3. So this is great. Using this relation, we now have a way to translate subtraction into a purely addition problem and flipping bits. I should say one thing that's kind of mysterious is this formula, that a plus negative b is the same as a plus flip b plus 1. It looks like it should be obvious, because the way we've defined minus b is as flip b plus 1. But one thing that you have to check is that this thing actually makes sense. I mean, if I had chosen a different representation of my number, I could have put anything here. For instance, if I had chosen 1's complement, then there would be no plus 1 here. But then suddenly the entire system would break and nothing would work. So part of the exercises is going to be trying to convince yourself that this formula is actually true. And there is genuinely something to prove here. It's not something that comes for free, even though you've defined negative b to be flip b plus 1. You have to show that 2's complement really behaves well with respect to addition. So keep this in mind. And the last thing I want to say is that there's a warning, which is that there's a notion of overflow, which can cause problems if you're not careful. So 2's complement can now handle subtraction problems, but there are some subtraction problems that it cannot handle. For instance, if I take negative 3 and I subtract 2, well, the correct answer to this question would be negative 5, but there's no negative 5 in this list. Negative 3 is 1, 0, 1, 2 is 0, 1, 0. So we could try doing the subtraction problem in the way that I described in the previous slide and see what happens. So first you take the second number, 0, 1, 0, and flip it and add 1. And then if you do this addition problem, you get 1, 0, 1, 1, and then you can ignore the first bit, and you get 0, 1, 1. But 0, 1, 1 is 3, and 3 is definitely not negative 5. So something strange is going on, and that has to do with the fact that you don't have enough binary digits to do this kind of subtraction problem. So when you do subtraction using 2's complement, you have to make sure that you have enough binary digits for the system to be able to handle the problem that you're trying to do. So this is something to bear in mind when doing 2's complement. But the upshot is we can now do subtraction on a digital circuit level by using an adder and NOT gates. Okay, so what do I mean by this? So let's go back a couple slides. I said that a minus b is a plus flip b plus 1. And I told you that flip b just means that b has all of its bits flipped. Or in other words, all of the inputs to b go through a NOT gate before going into this addition. So if I have a circuit that does addition, and I have a circuit that does flipping, which is just a NOT gate, which I do have, then I can just add these two numbers, and I get a new binary circuit that does subtraction for free. Of course, you have to add 1, and there's a nice way to do this if you're using the full adder system that we defined, using the modified 1-bit adder in the last video. So I'm going to leave this as an exercise to you. If you figured out the exercise on how to build a, let's say, a 2-bit adder, or a 3-bit adder, or a 4-bit adder, then you can try building, say, a 3-bit subtractor or a 4-bit subtractor by just using your adder and using your NOT gates in a smart way. And I've detailed a bit more about how to do this in the exercises. So now it's your turn. In the exercises, I've given you a problem which has to do with finishing the construction of the subtractor. Then I have an exercise which has you try to build something called a comparator, which compares two numbers and tells you when one is bigger than the other one. And finally, I've given you somewhat of a blueprint, and this is a challenge question, for multiplication. So multiplication is a much more complicated digital circuit, but if you do it in a methodical and systematic way, there is a way to approach it that is organized enough that you can still write down roughly how you do this on pen and paper. So this is the end of this week, and thanks for listening. I'll be back next time with more about digital circuits.